Okay, so the second example of balancing redox reactions is again using the oxidation number, but this time we are going to be in an acidic solution. So if you take a look at your notes, you'll see that we're basically going to just add a couple new steps to what we've already learned with the oxidation number in neutral solutions. And so here is our reaction that we are going to balance using the oxidation number method. So as always, step one is to put on our oxidation numbers. So let's go ahead and do that. Okay, now the second thing that we're going to do is figure out where the oxidation and reduction is happening. So we take a look at, again, I just go to the furthest left to the Cl, and we see that Cl is +5 on the reactant side and -1 on the product side. So it is involved in our oxidation reaction. And then what we want to do is we just want to figure out how many electrons has been lost or gained per Cl atom. And so we've gone from 5 to -1, which is 6. So 6, and actually I guess we called it in the previous example, we called this the, it's gained. So this is going to be a reduction. And in this case, 6 electrons have been gained per Cl atom. So then we move on to oxygen, and oxygen is -2 on the reactant side and -2 on the product side, so it's not involved. We're going to ignore it. And we look at the iodine, and it is 0 to +5. So that is the oxidation half. And in this case, it looks like we've lost 5 electrons per I atom. So I don't know how we can write it. Lost 5 electrons per I atom. Like that. Then what we do is the next step is we've just been, again, these numbers are just for the atoms. So now we want to look at the entire reactant. There's my first reactant, there is my second reactant. So we want to know how many electrons has been gained by this whole reactant, because Cl is just one part of the reactant. So we see, since we only have one Cl, the reactant has also just gained 6 electrons. Like that. And so when we look at this one, we see that one I atom has lost 5 electrons, but we've got 2 I atoms. So therefore, 10 electrons have been lost per I2. And silly mistake here, and it's very common for people to do this, is to put 5 electrons. Now that 5 electrons is just for one I atom, and since we have 2, I2 has lost 10. Then, like before, what we want to do is we want to find our LCM. And so what's the lowest common multiple of 10 and 6? And so if we multiply the two together, 10 and 6, we get 60. Divide that by 2, we get 30. So 10 goes into 30, 6 goes into 30. If we divide 30 by 2 again, we get 15, which none of these go into. So our lowest common multiple has to be 30. Draw our arrows. And then we just want to figure out 10 times what gets us to 30? Well, 3. 6 times what gets us to 30? Oh, that's 5. And then these are the coefficients for just our reactants in this equation. So we'll rewrite our equation Now, I've written the states in. It really doesn't matter if you put the states in or not, and I probably won't for the rest of this question put those states in. So now we know that this is 5, and we know that this is 3. So we're not going to ever change these numbers. We now know, and remember, we're just focusing on the atoms that have been involved in the oxidation and reduction, which is chlorine and iodine. So I'm going to look at chlorine. I've got 5 chlorines on this side and only 1 on this side, so I'm going to put a 5 there to balance my chlorines. I've got 6 I's on my reactant side and only 1 there, so I'm going to put a 6 there. Now, that has just taken care of my chlorine and my iodine. But we've got a problem here. We don't have, like in the last question, or the last example, the H's just worked themselves out. This time, if you count the number of oxygens on this side, I have got 15 O atoms. And my product side has 18 O atoms. Now, we don't want to go back and change any of these numbers up here. These numbers, 5 and 3, we figured out. That's it. Those are definitely the numbers. And the numbers here, 5 and 6 that we got as a result of these two numbers on the reactant side. So we can't change anything to make the O's work out. So we'll call this a problem. So problem, the O atoms are not balanced. So what are we going to do? Well, one of the reasons that I put the states in this example just right here, and as I said before, I'm not going to be picky if you write them or not, is these are all AQ, which means all of these are actually in water. So we have oxygen, other oxygens floating around in the water. So what step 6 is, and I'll write this down on the next page, step 6 is to balance the oxygens using water that is floating around. So balance O atoms with H2O. So I'll just rewrite the equation and leave a space here. You'll see why. Well, no, I guess we can do it right now. So if you look above, I am short 3 oxygens on the left side of this reaction, the reactants. So I need to add 3 H2Os to the reactant side. And I'm just going to rewrite this. And so sometimes what I do is I'll just put a square around this just to show this is sort of the This is the new thing that I've added to this equation. So now my oxygens are balanced, and this, we should write over here, is step 6. Um, we've got the oxygen balance. But now we got a new problem, and that's this. The H atoms are not balanced. Because I've got 6 on the reactant side and none on the product side. Well, that brings us to step number 7. Now, if you look up in the question, this is in an acidic solution. So up top, we said here that this was acidic. And if it's not written on your sheet, go to the top and write it in on the sheet. What this means is that for something to be acidic, it means that I've got H pluses floating around, which I haven't accounted for what I've done so far. So what I'm going to do now is balance the H atoms with H plus. So I'm going to rewrite the equation. You'll see that I'm going to have to add 6 H pluses to the product side. So I'm just going to rewrite what I've already got up there. But now I'm going to add the appropriate number of hydrogen atoms, which in this case is 6. So I'm going to add 6 H plus to this. And now it should be balanced. Now, one of the things that I suggest you do, especially in a question like this, is just go back and make sure that everything is balanced. And I'll show you what I mean by that. We want to balance the atoms. So I've got 6 H pluses on the reactant side, so 6 H's. 6 H's on the reactant side. I've got 6 H's on the product side. I have got 3 plus 15, 18 O's. 6 times 3, 18 O's on the product side. 5 Cl's, 5 Cl's. 6 I's, and 6 I's. Now the last thing you want to check also is your charge balance. Do we have an equal number of charge on both sides? So if we look on our left hand side, 0, there's no charge on water, no charge on I2. So we have to focus on this one right here, which is 5 times minus 1 is minus 5. So the charge on the reactant side is minus 5. On the product side, I've got minus 5, and I've got 6 minus and 6 plus. Well, these just become 0. 6 minus plus 6 plus equals 0. So I've got on this side also minus 5 as my charge. So I've got all my atoms balanced and all my charges balanced. I know that I've done this question correctly. Now, one of the things that's going to happen, and I'll show you sort of a way to prevent this from happening, is we have rewritten the equation 3 times now. And whenever you rewrite the equations, it's very easy to drop a negative sign. And what people are going to be tempted to do to fix it is to put electrons into their final balanced equation. So if I, for example, had forgotten this, it's not there now. When I add up this side, I do not add up to minus 5. So what people will do is do this. Well, I just need 6 electrons over here, because now 6 pluses and 6 minuses add up to 0. Then I'll have my negative 5 and negative 5. You cannot have, in the oxidation number method, in your final answer, electrons. So probably what you've done is you have gone and done this reaction, or sorry, rewritten this equation, this reaction, and you've just dropped a negative. So before you panic and think you've done everything wrong, if your charges don't match, just go back and make sure that you have rewritten your charges in there. It's very easy to forget those. Now, on a test, I wouldn't expect you to write the equation this many times if you didn't want to. This is how I would probably suggest you do it in your notes and on a test. So we'll go back to our original equation where we had 5Cl, O3, 1 minus, and I2. So we figured out what the numbers were for the atoms that were involved in the oxidation reduction, which is Cl and I. Like that. Now what I would do, instead of rewriting this, what I would do is go, okay, I know I've got a problem here. I've got 18 oxygens on my product side and only 15 oxygens on my reactant side. So I know I need more oxygens over here. And how do I balance them? With water. So what I would just do is don't rewrite this thing again. Is just put H2O and the number that you need, which in this case is 3, to the products, to the reactant side. Well, now that messes up your hydrogens. But again, don't rewrite the reaction. I've got 6 H's here. I've looked up here that it's in an acidic solution. So to fix my H's, I just have to go over to this side and add 6H+. And then we ended up where we were before. Just ignore that. We've ended up where we were before, right here. And we've only rewritten the equation once. So by doing it that way, you minimize the chance of missing a negative sign and then panicking at the end when things don't work out for you. And that is how we balance a redox reaction in a acidic solution.